For over a century, the internal combustion engine has defined human transit. We rely on petrol to give us rapid acceleration and high-speed commutes, while diesel provides the heavy, low-end torque required to pull commercial freight. The trade-off for that power is immediate and visible. Traditional combustion engines blanket our cities in dense, toxic smog. In response, we are actively searching for a flawless alternative. Engineers are testing compressed natural gas, refining waste plastics into synthetic oils, and scaling up electric vehicles to replace fossil fuels entirely. But the laws of thermodynamics dictate that energy transitions never come for free. Every single clean alternative we invent introduces either a severe engineering puzzle or a hidden environmental cost. Saving the environment is not about discovering a magical, consequence-free fuel. It is a strict balancing act of choosing which physical and mechanical compromises we are willing to accept. Compressed natural gas, or CNG, is an incredibly attractive option. It is primarily methane, meaning it burns incredibly cleanly and costs a fraction of the price of liquid petrol or diesel. The mechanical penalty comes from its physical state. Because CNG is a gas, it takes up significantly more volume inside the engine cylinder. As it enters the chamber, it displaces vital oxygen molecules before the spark plug even fires. Less oxygen in the cylinder means a smaller, weaker combustion event. An engine running on CNG automatically loses roughly 10 to 15% of its total horsepower. To achieve that eco-friendly footprint, a driver sacrifices raw kinetic performance and has to forfeit a large portion of their vehicle's trunk space to carry the heavy, thick-walled steel storage cylinders. Another highly anticipated alternative is plastic pyrolysis oil. This process melts down discarded landfill plastics and converts them back into a combustible liquid. It sounds ideal on paper, but pouring raw plastic oil directly into a standard petrol engine will destroy it within minutes. The liquid behaves more like a thick, highly viscous sludge loaded with acidic contaminants. To get the fuel to flow, mechanics must install inline heaters that raise the liquid to 60 degrees Celsius. This melts the solid waxy carbon particles, so they can pass through custom heavy-duty fuel injectors with significantly wider nozzles. Then, the engine's computer requires a complete retune. You have to retard the spark timing to prevent the low-octane liquid from violently misfiring and cracking the pistons. And because raw plastic pyrolysis oil contains high levels of hydrochloric acid, it will eat straight through standard rubber fuel hoses. Everything must be swapped to Teflon or marine-grade stainless steel. Even if the engine survives the burn, the exhaust is lethal. Burning unrefined plastic releases toxic chlorine gas and dioxins. To prevent a public health crisis, the factory catalytic converter has to be replaced with a massive industrial-grade exhaust scrubber. Managing this acidic liquid is so difficult that engineers rarely run it at 100%. Instead, they build dual-fuel systems. The engine starts on the liquid plastic, and once it is running, it introduces compressed natural gas to take over up to 80% of the actual energy load. Running a car on waste requires gutting the internal combustion engine and rebuilding its plumbing from scratch, making it an incredibly difficult technology to scale commercially. Electric vehicles bypass all of these internal combustion headaches entirely. There are no fuel lines to dissolve, no spark timings to adjust, and zero tailpipe emissions. But scientists do not measure an electric vehicle's impact by looking solely at the tailpipe. They use life cycle analysis, which calculates the environmental cost of a vehicle from the moment its raw materials are mined from the earth to the day the chassis is crushed in a scrapyard. The upfront cost of battery production is massive. Mining the lithium, cobalt, and nickel for a single EV battery requires digging up 500,000 pounds of earth. The transport ships carrying out this logistical chain burn thousands of gallons of diesel fuel. This chart shows the initial manufacturing carbon footprint of both vehicle types. Because of the intense material extraction required, an electric vehicle rolls off the factory floor carrying a carbon footprint 40 to 70% higher than a traditional petrol car. We are currently relying on the dirtiest, heaviest fossil fuel machines we have to extract the materials required for our clean energy solutions. That high initial carbon debt is mathematically accurate, but it is incomplete. This graph charts total lifetime emissions mapped against miles driven. A petrol car starts with a lower footprint, but pollutes constantly while in use. An EV starts with a massive carbon deficit, but runs cleanly. The EV mathematically pays off its manufacturing debt when those two lines intersect, usually around the 17,000-mile mark, or 1 to 2 years of driving. Past that exact intersection, the electric vehicle operates significantly cleaner for the remainder of its 15 to 20-year lifespan. The real ecological test lies at the end of that lifespan. Right now, global infrastructure recycles less than 5% of lithium-ion batteries. We are pushing millions of toxic chemical packs onto the road, and if buried in landfills, the chemicals will leach into soil and groundwater. Laboratory tests show we can recover up to 98% of the lithium and nearly all of the aluminum from dead EV batteries. If we successfully scale that technology globally, old vehicles will become the physical mines of the future, drastically cutting our reliance on heavy earth-moving equipment. Achieving a sustainable energy grid relies heavily on exactly how we measure impact. It requires looking past the illusion of a perfect fuel, understanding raw carbon math, and building the global infrastructure needed to actually close the loop.